Hello and welcome back to Calculus 2 for one last time, part 2, which is the U sub. We need to talk about U sub more. We've seen the basic idea. Basic idea is to replace part of the function with U, take care of the rest with the du, fix the constant if we have to, and then transform essentially our complicated integral into something that is easy and be done. Now, you can also have definite integral. And definite integral has limits. And those limits are x values because they come from x-axis. Those a and b are x1 and x2, the interval on x-axis. So as you transform function from x to u, as you transform dx into du, you better transform your a and b, which are x values, into u values. So now that adds an extra layer. However, the good thing is that you don't have to go back to x, because it's a definite integral which computes the number at the end. And if you transform the limits in u, then you will just use those values, because the integral will be in terms of u and your limits are in terms of u, so you don't have to go back to x. You can just compute with those new limits and be done right away. So let's take a look at an example for that. So definite integral. Let's do 40. That's the one of the cheapest problems we can find. So 0 to 2, 2x divided by x squared plus 1, everything squared. Easy, easy. So this is our integral. 2x divided by x squared plus 1. Now again, we're looking for function derivative pair first. And if I have that, then I can figure out what u is. So for function, I'm going to pick x squared because its derivative is 2x, which is on top. So that's great. So what's u? U is going to be x squared plus 1. And then du is 2x dx. Nice. I already have 2x dx. I don't even have to fix the constant. That's perfect. And now here's the new stuff. Your limit a is 0. Now that's x1. You plug that in the u substitution to get u equals 0 squared plus 1 equals to 1. So your transformed integral is going to have 1 as the lower limit. Your b equals to 2. So u2, which is the upper limit, is 2 squared plus 1, which is 5. And that's 5. We now see that we have 1 over u squared du. Now the entire integral is in terms of u, and limits are now in terms of u, so I don't have to go back to x values ever when you do the definite integral. So this is definite integral 1 to 5, u to the minus 2 du. And now this is u to the minus 1 over minus 1, computed from 1 to 5. No plus c, because it's a definite integral. So this is negative 1 over u, computed from 1 to 5. That's negative 1/5 minus negative 1 over 1. That's negative 1/5 plus 1, which is 4/5. And the answer is 4/5. So this is the entire problem, and what's new is in blue. You still have the same procedure. You figure out function and you figure out the derivative, right? The function derivative pair. And then you call your function u. Will include +1, so the whole thing can become just u, and then you have a square. 2x dx is du. You can write this if you want to as du over u squared, that's okay. And now the new part is for us to transform these limits. It used to be 0 to 2. You pick those are x values. So common sense, plug them in x. So 0 squared plus 1 is 1. And 2 squared plus 1 is 5. So that's why 1 and 5 are the new limits. So when you plug in the bottom one in the transformation over there, you come up with the bottom limit. And when you do the upper one, you come up with the upper limit. And then just follow basic integration. Your u is technically like x, right? You just plow for everything. You do not have to go back to x because you transform your limits. Now, if you do not transform your limits, then you have to go back into x and compute with those. So, technically it's up to you. I always encourage switching the limits because Calc2 is coming. And for some trig integrals and some trig substitution integrals, you really don't want to go back, because when you go back, the answer looks like 3/4 inverse sine of open parenthesis ln x plus 7, and then to compute that is just, right? Remember that all of those crazy complicated things look like this in U domain, which is why we have it. So get used to switching the limits if you are going to Calc2, so you are not dealing with inverse sine of ln of x squared plus 1 to compute 7, right? Where you can compute 1 or 0 and something like this. So that's the idea. We are doing the same problems, except we are transforming the limits, right, of integration from x domain into u domain as well, and then doing the 100% calculations in u domain. Let's have another example. How about 43? I know how much you love exponential functions. It is x squared e to the x cubed plus 1. Limits are from negative 1 to 2. Oh, I thought we swap. Wishful thinking. I give her the exams and the cough.
By the way, happy belated birthday.
Oh, thank you. Do you want the exam? I thought that was for me. Yes.
Thanks.
Yeah. Okay, let's at least figure out what's the function derivative pair. X cubed and x squared. Nice. So what's u? X cubed plus 1. Good. And du? Okay. Now I'm missing that 3, right? So I have to put 3 and 1/3. All right, let's see. So let's substitute. We have 1/3 integral. We plug in -1. So to transform the limits, let's do that blue. So u1 is -1 cubed plus 1. That's 0. And the u2, which is the upper limit, is going to take 2 cubed plus 1, which is 9. So the limits transform from -1 to 2 to 0 to 9. E to the u du, because the 3x squared dx, 3x squared dx is du. Let's color code that, so it should be clear. All right, so now 1/3 e to the u computed from 0 to 9. That's 1/3 e to the 9 minus e to the 0. How much is e to the 0? Yes. You do not have to go further and get the decimals and stuff. This is exact. It's fine. Just leave it there. Walk away. Or limp away, depending on your status of practice of this. You love trig, right? Few chapters are coming up. Sine theta over cosine cubed theta d theta. All right, let's go. So sine over cosine cubed. Theta d theta. Limits are 0 to pi over 4. What's u? It's either sine or cosine. Which one? Sine. Okay. Let's put sine theta, and then du to be cosine theta d theta. So now if you substitute, you get u divided by Now what? I have a cosine cube over there. To get a cosine cubed out of this one, I would have to solve for cosine theta, which is du over d theta, and then cube both sides to replace cosine cubed with du over d theta cubed, and that's as you can see, that makes no sense, right? So when you get to the point where nothing makes sense, you go back and you switch everything. So we switch this to cosine. There we go. Now we put -1. And when I substitute now, it will make sense. Negative sine, so that's d theta, divided by u cubed. Yay! Oh, sorry, du, not d theta. What now? How do I transform the limits? What should I do for u1? Cosine of 0, very good. So we take the function, the transformation, we plug in the lower limit in a transformation, we calculate and we get 1 for the lower limit, because cosine of 0 is 1. For the upper limit, u2, we have a cosine of pi over 4, which is? Very good. And now we're supposed to integrate. So let's write this nicely. Oh, by the way, do you see that root 2 over 2 is a smaller number? It's about 0.7. And this is one of those situations where you have the lower limit on top. So we have to swap them. And this is that formula which we talked about in the previous section, right? If you swap the order of the limits, then the negative sign appears in the front and it will cancel with the negative that it's there. So now this is integral root 2 over 2 to 1. So this -1 cancels with the negative that the formula gives when you switch the limits. This is u to the -3 du. So that's u to the -2 over -2 from root 2 over 2 to 1. I'm going to put this as a -1 over 2u squared from root 2 over 2 to 1. And now we just compute. When I plug in upper limit 1, I get -1/2 minus -1 over 2 square root of 2 over 2 squared. So this better work out nicely, right? A lot of stuff over here you can cancel, but let's just cancel these two. So -1/2 plus -1 over 2 root 2, that's it. So for definite integrals, you just have this extra calculation in blue. And you don't have to go back to x values. You can just calculate everything from the point of u. Because you switch the limits into u, and you just compute from there. The last concept is back substitution. And this one, in general, is tricky because you have to back substitute certain values. Let's see if I have the, let's say, integral of x square root of x minus 5 dx. Which is not a pretty problem. Looks very simple. But it's this technique now that has extra step. Sure, you can all integrate x. Sure, you can all integrate square root of x. What we can integrate is the square root of x minus 5. So we are going to use our good old substitution, u equals x minus 5. Right? That's our u sub. And then your du is equal to dx, because the derivative of x minus 5 is 1. So that's easy, right? Now, when you try to substitute this back, you see that there is still extra stuff in there. So if I substitute this back, I have square root of u du, right? That's not a problem. See, this x is still there. And the reason why this method is called the back substitution is because what I'm going to do, again, this is new, so I'm putting in blue, I'm going to solve for x here, and that's u plus 5. And that gets plugged in here. To spot this type of manipulation is tricky, especially when you are in a stressed environment. So the book only has like 3-4 problems on this, and this will pop up here and there. Nothing major. It's stuff that we did above this line. See the black line over there now, middle of the screen? Stuff above that line is 90% of your problems from this day on. 90% of your integration problems are going to be that. Something from what we did. Now, these guys are very rare, but when they, pop up, this is the way to do them. So you make the substitution, and then you have this just one extra thing lingering, and then you swap this, and you replace that x with that. So now, as you distribute, when you distribute, u times the square root of u is u to the 3/2 plus 5u to the 1/2 du. Now these are basic polynomial, right, terms. So we took polynomial-like. They are not polynomials, but polynomial-like. We deal with it with the power rule with the n plus 1, right? That's what I meant. So when you do the n plus 1, you get u to the 5 halves over 5. And notice that when I say halves, I write it on the top. Plus 5 times u to the 3 halves divided by 3. And then again on top halves. And then there's a plus c at the end because it's indefinite integral. Now, we are going to swap everything back to x. I have 2/5 u to the 5, u, it was what? X minus 5 to the 5 halves plus 10/3 x minus 5 to the 3 halves plus c. And that will be the answer. So for back substitution, you have to go and express x as a function of u, and then plug that in to get. So that's that. I hope you're not disappointed, but that's the u sub. It's the most frequent technique. It's backwards chain rule, and the game is to figure out function derivative pair, set function equal to u, and then the derivative should take care of du, and you can only fix constants. If you are short than x and you have x extra, you are making wrong choices. But you don't have to worry in a function derivative pair that the derivative of x squared is 2x. You just need to know that it's one order less. So x squared goes into x, x to the 5 goes into x to the 4. Sure, there are constants, but remember, the constants you can fix that issue, right, by putting a number inside and a fraction on the outside, or fraction inside and a number on the outside. So we can fix that stuff. And I think that's it for you sub. There is nothing else. They have a whole bunch of problems that you guys can practice. I'm talking 100 problems in this section. So, try the homework. Send me an email if you have questions. That's the course. Done. You lived through Calc 1 lectures. Bye.